And similarly, I2 current will also flow through the junction D and reach junction C, which means no current is entering into the galvanometer. If you connect two cells parallel to each other, the net current flow will be the sum of the currents of that particular individual voltage sources. So that can be represented in such a manner. If you connect two cells parallelly to each other, that means that the currents will add up together. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about Kirchhoff's rules. Now we are going to look at an applicational level of Kirchhoff's rules that is known as Wheatstone's bridge. So what exactly is a Wheatstone bridge? It is used to find out what is the unknown resistance connected to a circuit using a balancing condition. You might have used this in your PU labs such as the potentiometer. So you can say that potentiometer is an application level of Kirchhoff's rules. So without further ado, let's dive right into it. So what we have here is that we have P, Q, R and S, that is 4 resistors connected as shown in the figure, and that is connected to a cell using a key. So when the key is switched on, we have I amount of current going through this particular junction. Now what we are going to do is that we are going to apply the loop rule in this particular circuit and find out the balancing condition for this particular circuit. So first we have to identify what is the current coming out of this particular cell and going into the loop. So first we have the junctions at A, B, C and D, which means there are 4 junctions where current has the probability to split. So initially, when I amount of current is traveling from the battery, it reaches junction A. So when it reaches junction A, current split into 2 components, that is I amount of current splits into I1 and I2. So we can say that I is equal to I1 plus I2, which means one current which was initially I now split up into I1 and I2. Now that particular I1 and I2 are traveling through the resistors, which is P and R. So I1 is traveling through P and I2 is traveling through R. When it reaches junction B, I1 current is again faced with an option. That is, I1 current is again faced with an option to split. So this is I1 current and it has an option to split again. So we can see that since this is the galvanometer, it offers a resistance of capital G. Remember, in any circuit, that is any circuit, the resistance being connected represents the resistance offered by that particular equipment. If you're connecting a hair dryer, it will be the hair dryer resistance being offered. If you're connecting a toaster, it will be the resistance offered by the toaster. So here, this particular R is just a representation of the resistance offered in that particular circuit. So in this particular circuit, galvanometer is the one being connected, which means that the resistance offered is by the galvanometer. So we can say that G amount of resistance is offered by that particular galvanometer, and since this is a galvanometer, I'm going to call the current flowing through that particular circuit as galvanometer current denoted by Ig. So we can say Ig amount of current is going through this particular galvanometer. Now the remaining current, that is I3, I'm going to name it as I3. So I3 current is flowing through this particular resistor, which is Q. Again, here this I2 current reaches the junction D. Now the I2 current is not going to split here because already I1 current has split into Ig current and it is now traveling through the galvanometer, which means that Ig current will reach here along with I2 current, and Ig and I2 will together combine and flow through the S resistor, which means that I can call I4 is equal to Ig plus I2. So I can say I4, that is the current flowing through the S resistor, is equal to the combination of the current flowing through the galvanometer and the current I2 meeting at the junction D. They both meet at the junction D, combine together and flow through the S resistor. And now all this current, that is I4 and I3, meet at junction C, which means that all of these currents, that is I3 and I4, combine together to form I3 plus I4 is again equal to I. So here Kirchhoff's rule is obeyed because this is a closed circuit. So I amount of current entered into a junction through A and I amount of current is exiting from that particular junction C. So Kirchhoff's rule is absolutely obeyed here. Now what we are going to do is apply loop rule to this particular circuit. We are going to consider the loop, that is this particular triangle first, and then we are going to consider the next triangle. So first we are going to apply the loop rule in this particular loop, and then we are going to apply the loop rule in the next particular loop. So first we'll consider the loop A, B, D, A. So A, B, D, A. A, B, D, A, because it should be a closed circuit. That is why we are going back to A itself. Now we can see that what is loop rule? So we are going to take the current, the resistance and the EMF included in that particular loop. Since there is no EMF included in this particular loop, it will be equal to 0. So we can say I1, this is loop 1. So I1P. So how to apply loop rule is that we have to follow the direction of the loop, so that if any current is flowing against that particular loop, we will take it as negative value. So I1 is flowing along with the loop, so we can say that I1P is positive, and when we go down, this is IG. So IG into G is also positive because IG is the current and G is the galvanometer resistance, so that is also positive. And then when we return to the loop, right here we can see that I2 amount of current is flowing against our loop, which means we are going in this particular direction, I2 is flowing in the opposite direction, so we can say that I2 into R is negative because it is in the opposite direction. So this will be equal to the EMF in that particular loop, which is 0, because there is no cell connected in this particular loop. And now we are going to do the same for the next loop. I'm going to take this direction, that is clockwise. So I'm going to consider the loop BCDB. So in the loop BCDB, first again I'm going to consider the current, that is I3. So I'm starting from the junction B. So I3 amount of current is passing through Q. So I can write I3 into Q plus or minus. It is minus because I4 is in the opposite direction of the loop. So minus I4 into S, and again minus because when we are completing the loop, IG amount of current is flowing against the direction of the loop we are taking. So we can say it is IG into capital G, which is again equal to 0 because there is no EMF in that particular circuit. Now we applied the loop rule to two particular loops, and now in order to have a relation between these four resistors, what we are going to do is that we are going to consider a situation where no current is flowing through this particular galvanometer. So if no current is flowing through that particular galvanometer, it is known as a balancing condition, so that we can develop a relation between these four resistors right here. So we can say that for balancing condition, IG is equal to 0. This IG is equal to 0 is known as a balanced condition. So this is known as a balanced condition where IG is equal to 0. Now how can we rewrite this particular two equations? So if IG is equal to 0, the first loop becomes I1P plus IGG, that is IG0. So this entire quantity will be equal to 0, which means I1P minus I2R is equal to 0. And for loop 2, we can write I3Q minus I4S and this also becomes 0. So I3Q minus I4S is equal to 0. Now this is equation 1 and equation 2. So since the right hand side is 0 and there is a minus sign here, I can take these two on the other side and I can write this as I1P is equal to I2R, and finally I3Q is equal to I4S. So I1P is equal to I2R and I3Q is equal to I4S. So we have two equations right here, and in order to find out the balancing condition, what I'm going to do is that I'm going to divide this equation by this equation. So I'm going to divide 1 divided by 2. So I can write this particular equation as, so I'll get I1P divided by I3Q is equal to I2R divided by I4S. Now, why did I just divide these two? That is because when there is no current flowing through this particular galvanometer, that is when Ig is equal to 0, the current flow is that this current will flow like this and reach the junction C. And similarly, I2 current will also flow through the junction D and reach junction C, which means no current is entering into the galvanometer, which means I1 will be equal to I3 and I2 will be equal to I4. Same amount of current is reaching like this, which means that I1 is equal to I3, I2 is equal to I4. If these are similar quantities, then we can cancel them, so that we can write P by Q is equal to R by S. And this is the manner that we find the unknown resistance in a given circuit using Wheaton's bridge. That is, if these, let's say this is 4, this is 5, this is 6 and this is unknown, using this particular relation we can find out what is the unknown resistance. So remember, it is very simple. The only thing you have to do is that first consider a Wheaton bridge circuit and then consider the fact that we have to apply loop rule to both loops. And then when you have applied loop rule, the next thing you have to do is that you have to apply the balancing condition, which states that Ig, that is the galvanometer current, will be equal to 0. No current will be flowing between the two ends of the galvanometer. So we can say that applying the balancing conditions, I1 and I3 will be equal, I2 and I4 will be equal, which means that we'll have a condition so that resistor 1 and resistor 2 will be proportional to resistor 3 and resistor 4, which means P by Q is equal to R by S. And that is Wheaton's bridge. It is a very, 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 very important topic, constantly asked in your exams. So please pay real good attention to this particular topic. It is a very easy derivation. Numericals can also be asked regarding this. So please pay attention to this. Now there is one more thing that I have skipped ahead, that is combination of cells. We have seen cells being connected in many circuits, but we have never seen multiple cells connected in different arrays. That is, cells can be connected as series, that is one after the other, or they can be connected in parallel manner. So what is the difference between these two circuits? Is there any difference, or is it like however I connect the cells, I'll get the same amount of power? Maybe the power is doubled. Is it like that? Or is it like if I connect it in different forms, the power will be reduced or the voltage output will be reduced, halved or doubled? We never know. So in order to find out that, we are going to connect cells in series and parallel and find out what is the difference between them and what is the net current or voltage flowing through that particular circuit. Since this is a little bit mathematical, first I'm going to help you look at it from a logical standpoint of view and then dive into the mathematics. So the first thing you have to understand here is that if we have two cells, that is E1 and E2, connected parallelly to each other, let's say this completes the circuit. So this completes the circuit and they are connected parallelly to each other. then what will be the net current or voltage flowing through that particular circuit? So these two cells will have an internal resistance of R2 and R1 because they are cells E1 and E2 respectively. So they have internal resistances of R1 and R2. So logically thinking, what will be same here? Will the voltage be same or will the current be same? You can just use your logic and know that we studied in the loop rule that and the junction rule that current will be flowing from the positive end to the negative end, which means that let's say I1 current is coming through here, I2 current is coming through here, that is I1 current is exiting from the battery E1 and I2 current is exiting from the battery E2, then a junction B, they combine, let's say this is A and this is B, then a junction B, they combine together, that is I1 plus I2, let's call it as I. So you already see that using just logic, if you connect two cells parallelly to each other, that means that the currents will add up together. That means voltage will be constant. How much ever cells, it does not matter if you connect 5 or 6 or 7 or 8 cells like this, the voltage difference between these two terminals will be same. If you have, let's say this is E, you're connecting E value of voltages across this parallel cells, that is E2 equal to E1 is equal to E, then if they are identical cells, then the potential difference between point A and point B will always be just E. That is, if you connect the cells parallelly to each other, the voltage difference will be same, only the current flow will change. The currents will be added up together. So more current will be flowing through this particular circuit, but the voltage will remain the same. So assuming this, taking this into consideration, we are going to prove what is the equivalent voltage in that particular circuit, what is the equivalent current, what is the equivalent resistance in that particular circuit. So this is for the parallel connection. So we have two cells which are being connected in parallel to each other. There is a cell E1 and E2 having internal resistances R1 and R2 and they are connected parallel. So we know that in parallel connection, current is the factor which will be increasing and voltage will be same. So for series connection, it will be completely ulta. Current will be same, but the voltage will be going on increasing. Just have that in the back of your mind. So from the previous relations we studied about internal resistance, EMF and terminal voltage, we know that there is a relation that exists, that is terminal voltage is equal to EMF of the cell minus current times internal resistance of that particular cell. So this will be the equation in order to find out voltage, that is terminal voltage of this particular cell. But here we know that current is the factor which is going to increase. So we have to write this in terms of current. If voltage was the factor that was going to increase, we can use this particular equation. But here current is the factor which is going on increasing. So we have to find an equation in terms of current. So we have to write I is equal to epsilon minus V divided by R. That is, I will stay here, R will go to downstairs, epsilon will go to that side, which means I is equal to E minus V by R. So we know that current will be coming out like this. Let's say I1 and I2 are coming, which means I will be equal to I1 plus I2. So current will be adding up. That can be written as, that is, I is equal to I1 plus I2 can be written as E1 minus voltage is not changing divided by R1 plus E2 voltage is not changing divided by R2. So this is the net amount of current flowing through that particular junction. If you connect two cells parallel to each other, the net current flow will be the sum of the currents of that particular individual voltage sources. So that can be represented in such a manner. Now what I'm going to do is purely mathematical. What I'm going to do is split up this equation so it is more easy for you to understand. So we can write E1 divided by R1 minus V by R1 plus E2 divided by R2 minus V by R2. Now what I'm going to do is cross multiply this and have a neat equation. So this again, I'm going to rearrange this particular equation and I'm going to write this particular equation as all the E1s in one place and all the V's in one place. So I can write it as E1 by R1 plus E2 by R2. So E1 by R1 plus E2 divided by R2. So that is together minus, I'm going to take the V here as common factor because here also it's V, here also it's V. So I'm going to take it outside so that it is V into 1 by R plus V into 1 by R plus 1 by R2. So I can write this as 1 by R1 plus 1 by R2. Now I'm going to simplify this equation once more by cross multiplying. So I can write it as E1 R2 plus E2 R1 divided by R1 R2 minus V into, either you can keep it this way or you can cross multiply it, it's up to you, R2 plus R1 divided by R1 R2. So now we have a condensed equation, that is this particular equation in terms of I. So this particular equation is now written in this form, that is I is equal to the net voltage, that is EMF in that particular cell minus the voltage factor and divided by the internal resistance. So we have that particular equation. Now what we are going to do is that we are going to write this particular equation like this one because we want to find what is the equivalent EMF and equivalent resistance. For that we are going to write it in terms of voltage. That is very simple. The only thing you have to do is bring this term here and bring this I here. So this V into R2 plus R1 divided by R1 R2, you're taking it to the left hand side and you're bringing the I to the right hand side so that you can write this particular equation as V into R2 plus R1 divided by R1 R2 is equal to E1 R2 plus E2 R1 divided by R1 R2 whole minus I. So now we have it in terms of V is equal to, but we want it purely in terms of V, that is only V is equal to the net EMF minus current times internal resistance, which means this internal resistance factor also I should take to that side, which means if I take it to that side, meaning if I multiply with reciprocal, this will be flipped. So I can write, when it goes here, it will be R1 R2 divided by R2 plus R1. It will be flipped. So I can write V is equal to E1 R2 plus E2 R1 divided by R1 R2 minus I into R1 R2 divided by R1 plus R2. That is, when I take it to that side, it is just flipped. So now we have a pure equation that is in terms of voltage. That is, V is equal to E minus I times R, which means that I can relate this particular equation with voltage and internal resistance. Because I is there, this is the internal resistance term and this is the net voltage term, which means that V equivalent, that is the total voltage, will be equal to the net equivalent, that is E equivalent, that is the net EMF in that particular circuit minus I times R equivalent, the net resistance in that particular circuit. So we can say V equivalent is equal to E equivalent minus I into R equivalent, which means that these terms are now relatable, which means I can compare each of these terms. This E equivalent will be equal to E1 plus E2 plus like that, because it is, this particular term is nothing but E1 by R1 plus E2 by R2. This is just being cross multiplied. That is why it is looking like this. But we can write this as E1 by R1 plus E2 by R2, which means that E equivalent will be E1 plus E2 plus E3 plus etc. That is E equivalent will be equal to this particular term, that is E1 R2 plus E2 R1 divided by R1 R2. That is simply E1 by R1 plus E2 by R2. This is the net EMF of that particular cell, and resistance, that is internal resistance, will be equal to again R1 R2 divided by R1 plus R2. R1 R2 divided by R1 plus R2. But we also have to find what is the net current flowing through that circuit. But we know that I is equal to V by R. Using that particular relation, that is Ohm's law relation, we can take the relation that is E by R will be, that is E equivalent by R equivalent will give you the net current flowing through that particular circuit. So that I'm going to divide this particular term by this particular term, that is E1 R2 plus E2 R1 divided by R1 R2 whole divided by R1 R2 divided by R1 plus R2, which means that this R1 and this R1 R2 will both get cancelled, and this R1 R2 will go to the numerator, so that we can write this particular equation as, this can be written as E1 by R1 plus E2 by R2 plus E3 by R3 plus etc. up to En, which means that if there are n number of cells, being connected like this, then regardless how many cells are being connected, it will be equal to the ratio between the EMF of the cell and its internal resistance being added up, which means that the net current value will go on increasing. This particular thing is nothing but I1 plus I2 plus I3 plus I4 plus etc. up to In, which means the voltage will be same. If we have identical cells, that is if I'm using E everywhere, that is if I'm using 9 volts, 9 volts and 9 volts, that is identical cells that is being used, then I can say that the potential difference between these 2 points will be 9 volts. Or if I'm using E, that is the same voltage throughout, then I can say that it will be N times E divided by R into N. The N's will cancel out, it will be E by R. That will be the net voltage in that particular system, that will be constant. That is the way we find out the equivalent EMF and internal resistance of a cell connected in parallel connection. Now what about in series connection? So we saw that for parallel connection, current was being added up, which means that if you are connecting in series, you should remember here the voltages are being added up, which means current flowing through this particular 2 cells are the same. That means if I have a connection like this, E1 and E2 being the EMFs of the cells I have connected, R1 and R2 being the internal resistance of the cells, then I can say that the EMF, that is the terminal voltage, the voltage factor will increase, but the current flowing through each of these cells will remain the same, which means that if I am taking A, B and C, that is I am considering 3 junctions, A, B and C. These 3 junctions split E1 and E2, which means the voltage between A and B is different and B and C is different if I'm using different cells. So what will be the net voltage between A and C? That will be equal to the sum of these 2 individual voltages. That is, we studied in the second chapter also that voltages or potential differences add up. So if I'm taking a voltmeter and I'm measuring what is the potential difference between these 2 points, that is VAC. What is the potential difference between VA and VC? Then I can say VAC will be equal to VAB, that is the potential difference between these 2 points, that is the potential of E1 plus the potential of E2, VAB plus VBC. That will be the net potential difference in that particular circuit, that is between A and C. So we can write this as E1 minus IR1 plus E2 minus IR2. Why? Because we know that V is equal to E minus IR. We know this particular relation. That is why we can write it like this. Now I'm going to collect all the EMFs together and write all the internal resistance together, so that I can write it as E1 plus E2 minus I into R1 plus R2. So here directly I can write E equivalent. The equivalent EMF will be E1 plus E2, while R equivalent will be equal to R1 plus R2. So we can clearly see that here the voltages are being added together, and this is how we add the equivalent resistances. So here the voltage is being added together. If you connect a 9-volt battery and a 9-volt battery, the net potential between these 2 points will be 18 volts. If you connect a voltmeter between these 2 points, the reading will say that it is 18 volts. Given that the internal resistance and resistance of the wire, everything is very low, you will get the potentials, that is the voltages, being added together. So this is how you add or view the equivalent EMFs in a series connection. So we saw how to add in parallel and we saw how to add in series when cells are being connected in that particular fashion. So if you want more voltage in your particular circuit, you should add them in series. If you want more current in your particular circuit, then you should add them in parallel. So that is how you connect cells in series and in parallel. The only thing you have to remember here is that here it is plus sign. But if ever the battery is flipped like this, this will be a normal circuit. But if ever the battery is flipped like this, then the EMFs will cancel each other out. Instead of E1 plus E2, it will be E1 minus E2, because the direction of the current has now changed. Just like in the loop rule, if the direction changes, the sign also changes. Just one small thing to keep in mind. I hope you have understood all about cells in combination and Kirchhoff's applicational rule, that is the Vidhyaashram's bridge. I'll see you all in the next chapter. That is, the chapter is finished, and I'll see you all in the next chapter with more interesting physics, explaining what happens when charges move. Thank you.